Just a brief introduction to a lot of the interactions that we're having with UNSW recently. We do 2 joint venture style research degrees with UNSW with the computational design degree. In particular, the honours degree, which a lot of you will probably know Madeleine and Nazmul through. And then we also do a graduate research project. We provide a student with a research question and we guide that student through their research for 3 months. And so that particular student this year was Emily Leung. We were very fortunate to have Emily as our student. So we gave her a rather difficult challenge into looking at how we can revolutionize our own digital tools. So that she'll be presenting that, developing delocalized open source architecture-centric tools. And then Nazmul and Madeleine will be presenting their complete honours research for the year. And I believe they were successful with a, what was it? First class honours or something. Yeah. So that's a really good outcome for both them and us. So I'm going to hand over to Emily. Just a warning, this might seem a little bit technical, but she does a very good job of explaining the broader concepts throughout the whole thing. So I'll hand over to Emily.
My name is Emily, and closer? Okay, sorry. So I'll be presenting my thesis on developing delocalized open source architecture-centric tools, a research project done in collaboration with some of the computational guys at Cox Architecture. So, for those of you who don't recognize this here is Minecraft. It is a single and multiplayer online game that allows you to fly around and build anything using blocks. The reason why I bring this up is because of how powerful it is in multiplayer mode. In multiplayer mode, you can work with or converse with anyone in the world at the same time within the same seed, which is the ID to a particular world. So I could build a house in that space and someone else could break it down or modify the house as they please. And so there's this level of collaboration. This idea of making changes and everyone seeing these changes instantaneously is something only the web can do. And it's already happening within web applications like Google Docs and Google Slides, where you can work together to edit things in real time. And so the rise in emerging technologies that use data have contributed to the success of communication all over the world. Social media, collaborative documents, and the gaming industry have already taken advantage of the web to provide synchronous communication and updated information on a number of mobile devices. In contrast, existing methods of communication within the architecture, engineering, and construction industry require additional platforms such as emails and verbal communication in conjunction with the 3D model in order to inform changes made by stakeholders. In addition, duplication of files and limited accessibility to the latest version contributes to the myriad of inefficiencies derived in existing practice. So for those reasons, the research question for this thesis is, in what ways can participating in building open source and dynamic web applications be developed to enable synchronous relationships between data and 3D geometry to optimize communication practices in the AEC industry? Now, that question is a bit of a mouthful. To break it down into simpler terms, what the question is asking is, how can we achieve the same successful outcomes of an online multiplayer game like Minecraft, where stakeholders can contribute and dynamically edit a common 3D architectural model so that it is up to date, readily accessible, and has the ability to be dynamically changed in real time? Now, don't get me wrong, there are a number of existing tools out there that seek to enhance collaboration and address issues of version control, file storage, model viewing, and commenting. And from my research, these are the main contributors. But what's interesting to note is that each provides various benefits and downfalls. To begin, out of this list, These are the ones that allow users to view and interact with the models on the web. However, from this resulting list, these are the programs that implement open source JavaScript library 3JS. So even applications like Autodesk 360 BIM use open source technologies on a paid subscription basis. And finally, out of the last 5, Flux and Platypus are the only 2 applications that combine all 3 aspects, but more importantly, seek to enhance collaboration through the web. But even then, Platypus is accessible only through Rhinoceros and Grasshopper, and when the session is closed, the data is removed immediately from the online server. And Flux? Well, Flux is mainly used to push and pull data between external programs, which still creates multiple files for the same model. In saying that, Flux is still quite powerful because it does store data from multiple programs on its database, even when the programs are not being used. So from there, we looked into some existing scholarly research into what people have said about this topic. Firstly, research into Minecraft was done to compare the success of multi-user CAD. More specifically, it showed a distinct opportunity to enhance collaboration when the platform is repositioned onto the web. But not only should a 3D centralized model on the web be a space to communicate ideas, but you want to be able to access information generated by others, which brings up this idea of the federated single point of truth. In other words, a common data environment that allows users to be able to obtain up-to-date information from various stakeholders. Current practices within architecture limit the ability to be flexible with the digital tools available. The software that architects use are not designed by them, but by computer scientists, which makes it quite limiting to them. Consequently, the sheer fact of using architectural software means already to operate like an engineer. So what if the architects understand and even author the tools that influence their process? Potential unprecedented discoveries could emerge. And this idea is also emphasized in the essay Hackers and Painters by Paul Graham, who draws upon the significant connections that creatives, such as architects, have very similar processes to hackers, which is this idea of making. So when we eliminate the cathedral model when building software to the open source development model, the bazaar, we can attain full effect of collaboration when being open to allow input from people across multiple disciplines. And this concept highlights the success of collaboration to be possible in today's digital age. So, as the first step into attempting to achieve the development of such a platform, the first prototype looked into the possibility of building 3D scenes on the web using building information models. This particular workflow suggests a number of steps of exporting and importing, as A-Frame requires specific types of model files to be referenced within the HTML document. So this is the initial result of importing the model. You're then able to add interactivity and data attached to the object, where the user is able to navigate around the space, select objects in the scene, and the associated data is previewed on the sidebar on the left. So the problem with this tool, though, is that its main function is for visualization purposes only. Any changes must be made to the external model, which is then exported a number of times before synchronizing it back to the web. So the next step was to move forward into finding an alternative solution, and that was inspired by Google Docs, where you have Google as a database, the collaborative application is Google Docs, and the data that the multiple users are editing is a text within the document. Redback BIM is the application that we've been building, and we've used Flux as a database. As I said, Flux is able to store data on the web, and the data we are changing is the geometry. We can't directly edit geometry like that. Geometry in Flux is actually made up of a JSON string. And so to bring you into what JSON is, which is short for JavaScript Object Notation, it is data in its simplest form made up of a key and a value. And Flux works exactly the same way, in that in the Flux database you have a project, and within that project you have a series of keys, and within those keys are values such as integers, strings, and even geometry data made up of a JSON string. So we revised the workflow for Redback BIM to allow multiple users to push data from compatible architectural software to Flux and preview, interact, and edit the geometry in their Flux viewport, which is made of 3JS, as well as pushing data into React components so that the users can interact with the model through the application. With the help of Kyle Maxwell, an engineer from Flux, he was able to put together a sample open source React application which could interact with the Flux SDK. And from here, we built on top of this application. The initial idea for Redback BIM was to simulate the application towards a 3D modeling program, where you would select an object and edit its properties. The first attempt was to achieve that through converting the JSON string of a geometry into a table of attributes, where the user could potentially edit the values. However, what you'll find with the way Flux.json is structured as shown on the right is that the areas highlighted blue suggest that the data is nested. And so what you'll get is object in the data table, as well as the inability to edit the table directly. So going back to the drawing board, research into alternative solutions led to using a JSON tree component that would allow for editing. And these are the few open source JSON tree components that were appropriate for the situation. But from my experience of implementing these, the last one on the right was the one I used, as the rest lacked documentation for me to understand how to use it. And as a result, what you'll find is on the left is what the sphere's JSON influx is made of, and on the right is the same data being pushed into the JSON tree component. And in this JSON tree, as a user of the application, you're able to edit the values such as the radius, adjusting the color of the sphere. You're basically editing the geometry directly within that application. So this is the result of the prototype. All right, so it sits in Flux as a web application. You open into it, you can select a project, and you can select a key. So we're basically choosing the same cube. The left is a Flux website, and when I hit raw, it shows the JSON string data that makes up the cube. I'm changing the value within the JSON tree, and it's updating it in real time. Okay. So that's pretty much what's happening, and it proves that it is possible that you can edit geometry in real time on the web, and everybody has the ability to see those changes instantaneously. So Redback BIM is available as an open source web application on GitHub. The reason for that, again, as I stress, is because there's potential to continue to personalize it and make it even better, to allow people to tinker with it and make unprecedented discoveries. There are obvious limitations with using a JSON tree to edit geometry on the web, but it is a part of the process. This is one step as a proof of concept, a step closer to being able to actually collaboratively build 3D architectural models on the web. So let me bring you back to the beginning with the inspiration of Minecraft. Even though it's not accurately the same, the implications are very much there. It's getting close to being a synchronous, collaborative workspace where you can stream, store, and modify a model in real time. And that's what we wanted to achieve in the first place. Future work. Obviously, there is a lot of work, and I do hope to be a part of it. It could be research into user testing, definitely applications in practice, testing it on a number of devices and projects, functionality, adding more functions. Flux has a viewport documentation that allows you to put in functionalities like clipping planes and enabling shadows. And in terms of software, maybe make it even more relative to how architects use programs for creating drawings, downloading files ready for 3D printing, even generating visual scripting tools. That could be a potential step in the process. In conclusion, this research is a step closer to building live architecture-centric applications on the web, contributing to the potential to optimize communication practices and ultimately focus our attention to solving real-world problems. Thank you.
So the research that we did this year is called Adjudicating by Algorithm, and within that we actually made 2 separate papers, even though we did it together. So my paper was called Scripting Regulations to Generate Permissible Forms, and Madeleine's one was called Creating a Web Platform for Interaction with the Law.
So our research started with the focus on the relationship between computational design and urban planning. So urban planning decisions inevitably shape the environment we're in. The rationale behind the research was to ultimately create better urban planning decisions through the lens of computational design. So by looking at the integration of computational design techniques and urban planning, new workflows for preliminary design processes could be created. So when we look at problems in urban planning, zoning maps that define the legal boundaries of the law are two-dimensional and fail to clearly communicate the legislation such as FSR and HOB. So this makes development costly and time-consuming. So in Sydney, the current local environment plan, or the LEP, is provided in hundreds of PDFs online, and that each map is in a separate PDF, which makes it quite difficult to interpret. So in an interview with David Harron, the senior planner at the New South Wales Department of Planning, he explained that these LEP datasets are quite large, and that the LEP refers to are longer than the actual LEP itself. So one layer of information for an area could be 20 sheets of PDF, but when you consider land use maps, heritage maps, and FSR, it can get quite lengthy. And an interesting quote he said in the interview was, essentially, if you want a modern planning system, you need modern tools and a modern way of thinking about it, and that's digital.
So a similar problem is faced in the field of law in general, where the sheer number and size of regulations becomes daunting. This is mainly due to the fact that laws are written in language, in legal prose, which tend to make them pages and pages long. So computational law is the idea of embedding logic of laws into computer systems which automate legal decisions. It's a field that already exists as a response to the problem. So if we think of tax, like an online tax system where you put in the correct information and then it fills out the right forms and gives you the right obligations, then that's an example of a computational law system. So we can borrow the same overarching idea of computational law and apply it to urban planning. So our research sticks to this theme of law as code, which is the concept of converting laws into logic, which can then be processed by a computer. So it's an alternative to the current documentation of laws in legal prose, and suggests that the computer is actually determining the laws rather than a list of like a whole paragraphs and paragraphs of words. So with that in mind, we came up with 2 research projects. My one was to translate building regulations into a script to generate building envelopes. That was in the perspective of the people who actually make laws, so policymakers, and so they can sort of foresee the laws as they change them. And Madeleine's project was to create an open source decision support system, which is from the perspective of designers and developers to see whether to interact with the building envelopes and to see how designs comply. So these are the 4 tools we made as a result of this research. They're all named after whales and a dugong. Just so I don't sound crazy talking about whales, just letting you know what the switch is. So we'll go through each of them later on in the presentation. But I worked on 2 of the tools while Madeleine worked on the other 2, and they all came together to make sort of one package. So this is a diagram we'll also be referring to as we go along, just so you understand the computational workflow between each tool. I'll explain it later, but just letting you know. So my objective when making this research was to create a script that encodes building regulations and use it to generate permissible building envelopes. So the first question to ask is, what is a permissible building envelope, or what have we defined it as? So we've defined it as sort of the maximum buildable area on a property. It includes the appropriate setbacks and heights. It's important to note that it could change based on different land uses and different and bonuses, but we haven't considered that and just considered the permissible building envelope as the first phase of testing whether a building is compliant. So this brings us to Beluga, which is the Grasshopper script that generates the permissible building envelopes. And when we talk about scripts, there's generally 3 things we have to consider: the inputs, so what we need to start off with, the processes that happen to the inputs, and the third one is the outputs, which would be the building envelopes. So what we need for inputs for our script were the cadastral lots, the right LEP regulation. So for the sake of this research, we just used height of building and FSR, sun planes, and the setbacks. So as Madeleine mentioned, the LEP is provided online in PDFs, which was not the best format. I'm sure if you ask anyone in the CDG, they don't love PDFs. But luckily, they're also available online on a website called Oren, which gives them in a GeoJSON file, which is a GIS format. So we're instantly stuck with this problem of the integration between softwares and disciplines in general, like not even just in urban planning, but in the built environment, that the flow between them is limited. So ideally, we should be able to get a file and be able to use it in whatever sort of software that we have. So that leads us to our second tool before we could even start our first tool, which is Humpback. So Humpback is a GIS translator. It converts between GIS file types and Grasshopper. So what we used is GeoJSON, which is similar to what Emily was talking about. It's similar to JSON, but the difference is that it's in reference to the Earth's surface, so everything is geolocated, so it uses longitude and latitude. So what you can do is define a geometry by its coordinates, and then associate the correct, keys and values to it. So we can say that the type of shape is a polygon, we can say that the color is gray, and that the height is 80. But those don't really mean anything until it's interpreted by a software. So this is why it's used in WebGIS platforms such as Google Maps or OpenStreetMaps, because it's so easy for humans to read and easy for machines to parse and generate. So Humpback's idea was, as I mentioned, to connect GIS with Grasshopper. So what we did was we created a series of tools. I think there were 5 in total, but 2 main ones. One was to convert between GeoJSON into Grasshopper geometry, and the other one was to do the other thing, like the reverse, to create Grasshopper to GeoJSON. Did I say that in the right order? Cool. So what we did was, since we had Cox as the industry partner and we wanted to use the tool set outside of the research, we decided to make it we decided to rather than make it very specific, we decided to make it a tool set that anyone could use. So we uploaded it to Food for Rhino, which is a website, sort of the app store for Grasshopper, where you can upload tools. And so far, I think we've actually used it in some projects. Madeleine used it this week. I think Rob's used it. Mitch has used it. Beck have used it. We've used it in a few projects, which is kind of cool. So with that, we've gotten the cadastral lots, the HOB and the FSR. We've used Humpback to convert it into, to bring it into Grasshopper, and now we can continue with our script. So we can start making the script that generates building permissible envelopes. So the first thing in the script, in Grasshopper, is to associate the correct policies with the right lots. So that's a pretty simple process. All you have to do is test whether they're colliding with each other. So the HOB is drawn as a boundary. If your lot is within that boundary, then it inherits that property. So that's pretty straightforward. But it gets a little more tricky when you're dealing with things such as front faces, back faces, side faces, which all have different setbacks in the DCP. So what we've done, and the benefit of actually coding this stuff, is that you can make a script that determines what a front face is or a back face. So it's no longer it's no longer vague, there's one outcome. So with that, we got a very small section of, I think this is near Circular Quay, so a small section of Sydney. We've determined what faces are which. We know the right height of building for each, and just with that, you can make a really basic building envelope. So what we did was we got the property, we extruded it up to 45 meters of height, then we set back each face according to the DCP, and then we continued and then cut it off once it reaches the maximum height determined by the HOB. So once we had that, you can start adding in more regulations to make the geometry more complex and the envelope more accurate. So we added in sun planes. I actually manually draw those in. That wasn't available online as 3D, so that was a pain, but oh well. So if the sun plane intersects with the envelope, it gets a new height, so it gets pushed down. And then on top of that, we also included FSR. If you look at, can I point with this? Yes. So if you look at this building in the middle and the building below, the FSR on the image above is actually greater than the one below. So what's happening is the HOB determines the maximum height it can go, but the script automatically makes it create the highest building that it can. So if the FSR is low, what it does is it reduces the podium and lets it extend higher, but it doesn't go, it's not there, okay. So with that, we've created a very basic script that creates building envelopes. And the next step was to apply it to a larger area. So we did a larger portion of Sydney. Since we had the actual we had the floor for each level, we were able to produce very basic statistics, so the GBA, GFA, and we associated a specific percentage for resi and com, and from that we got dwellings and jobs. Also, just for fun, we chucked in a facade generator, which just gives you a very basic facade. It's a bit ugly, but it gives you sort of an indication of what it would look like. Yeah. All right, so just to go back to this diagram. So what we did was we got the LEP data from Oren. We used Humpback to convert it into Grasshopper geometry. And then from Grasshopper, we were able to create the building envelopes. And then from there, we can send it back into Humpback to convert it back into a WebJS format. So I'll let Mandy take over from here.
So in preliminary work to Dugong, we developed an app that allows users to visualize their own geometries within a web server. So you can generate your own geometries in Rhino and then convert them with Humpback to a GJSON, drag and drop it onto the site, and it visualizes with embedded information. So this could be useful for showing urban schemes to clients so they can interact with the map. So my objective was to develop an open platform for laws to be found and developers to work within. And it's the third tool in the series. So when starting Dugong, the concept was to create an open source web app that works as a decision support system. So web apps allow basically they spread computational tools. So it's quite complex to visually script, but this allows those processes to be embedded in a web app with a simplified interface, so more people can be able to use those functionality. So what happens when you go onto the website? You find the site that you want to select. Site information comes up of the lot. So at City of Sydney, we can see what the height of building is, the FSR, the land use, and see if it's heritage or not. And then we can also change the site envelope transparency. And then we can draw our own geometry straight onto the map. And then we get a live feedback of the feasibility study, so the height of building, the levels of the building. So we can create multiple blocks to develop a quite complex form and have a quick feasibility study of that. So we extrude it and then add properties, and we can see when the FSR goes over, it turns red, letting you know that the design is outside of the constraints. And then we can save the building online. And what this does is save the GeoJSON to an online server, which can be accessed later and then brought into Grasshopper. So in a similar schema to Dugong, DA approval could be streamlined through a web app. So a 3D model of the development could be submitted to a site like Dugong, and an immediate analysis of the file could check the buildings if the building complies and flag issues such as height, FSR. Furthermore, through these explicit checking processes, transparency between planning processes and the community is improved. So an automated processing could aid in rapid yet considered urbanisation, and laws are tested before they are implemented, and developers can receive accelerated pre-approval. So Dugong is an example of how the laws can become visible and how the law represented in 3D can make it easier to communicate legislation. So in an interview with Peter Holt, a planning lawyer, he said the 3D law could have many benefits for developed multi-strata cities, such as Singapore and Hong Kong. So an example of an area where this is maybe needed in Sydney is the arcades underneath Town Hall, where due to 2D planning systems, they're actually considered a park instead of commercial, which may make it harder to sell the asset further on because of the ambiguity of the law. So 3D law and algorithmic law have been shown to benefit the government and society if implemented correctly. So Peter Holt also brought to our attention the Rocks redevelopment scheme. So it was the only case study in New South Wales with a drawn 3D envelope of the law. So the extents of the envelope were hand-drawn in axiometric to communicate the maximum building form. And as a result, the Rocks has an explicit outcome that developers can work within. So even though these envelopes do not compute the height and FSR such as Beluga, it is a much more straightforward way of communicating the law. And then we come to our last tool, which is Minky. So Minky is a versioning tool for Grasshopper that can be used to access and save iterations of 3D and algorithmic law. So versioning control is a way of recording changes to a system where every change can be tracked. Changes can be suggested, and each version is saved and can be rolled back. It allows for every version of the file to exist at the same time. So in software version control systems such as GitHub, allow developers to easily collaborate, and this is called a gist. So rather than translating language from English to computer code, when a gist is uploaded, an algorithm runs over the text, highlighting what changes have been made from one version to another. So an example of where this has happened in the law is from a software developer called Vermeer, who downloaded all of Germany's laws and then uploaded them to GitHub. And what this enabled them to do was to see the changes of the different legislations made explicit. So Minky works by taking a gist stored online from Dugong into Grasshopper, but it can also take the 3D form of the law from Beluga and save that in iterations. So using the link generated by Dugong, we can import the GeoJSON with Minky and convert it to usable geometry using Humpback. So this allows us to develop the sketch further and streamline the preliminary design processes and feasibility study. And this completes our life cycle. So with computational design techniques, open data from government resources can be interwoven with computational processes to create an algorithmic translation of building legislation. Humpback facilitates this by enabling GeoJSON to be imported into computational tools and GIS web apps. If I go back to here. So Beluga translates the law into like a visual script, and then Humpback again allows the transfer of data in between interdisciplinary platforms. And then Dugong communicates the law explicitly and interactively for built environment designers. So this interface allows fast prototyping and experimentation. So designs are swiftly analyzed for their feasibility as a building, and then Minky imports it into Grasshopper. So therefore, more time can be spent on design and less on analysis. Which one?
All right, this is just an overview of what we did. So this is the website Oren. We downloaded the LEP data. And then we brought it into Grasshopper. And then using our tools, we were able to get the geometry. This is just what it looks like in Rhino, just a bunch of boundaries with the appropriate data. This is Beluga, the script that generates the building permissible envelope. Each one of these components sort of represents its own regulation, and then just that stuff is just producing all the statistics. So after that, you can export the file and then put it onto the WebGIS platform Maddie made. If you click on a property, you can see what controls actually generated it. And these are just some iterations when you play around with the controls. So the benefit of doing this is that you can sort of test policies. This is just another website that that's live right now, and it shows different iterations generated from the script, and you can stack on different policies to see the differences between them.
And then this is just Dugong again. So selecting the site. And we can see the site information. And then you draw your own geometry onto the site and then get a live update of the feasibility study. So we've got the height of building, levels of building, FSR, and GFA and GBA being analysed. And then the building is saved out to a gist. Yep, and then it's online on GitHub. So this research is significant for a variety of reasons. So within architecture, streamlining complex analysis allows the designer to deliver tasks in a shorter amount of time. So the routine elements of the design process can be automated so the architect can further focus on problem solving and articulation of design. Additionally, the 3D form of the law can help guide policymakers in the processes of creating and maintaining building legislation, and the parameters of HOB, FSR, and sunplanes can be manipulated to display different versions of the city under different conditions. Thus, the complex relationship between each policy and their influence on the final form can be analysed. So this framework can be used to test urban policies before they're implemented.
Yeah,
Thank you.
But just to also let you know the significance of this, both these presentations in the international research field. Madeleine Nazmul have presented recently at UD, which is Urban Development in Gold Coast, and also the paper was presented by Hank Hausler in Singapore with the Urban Planning Conference. Doesn't really matter what it's called, but as well, this honours has been put into various other international conferences, or not? No. Three others, and they're it's been through three. And Emily's particular paper, the abstract's been accepted in an international CADREA conference, and so it's highly likely that will be being presented next year somewhere in Asia. So.
A lot of reasons behind this, right? So Andrew has made something called Wobbegong, which is
And Mitch.
And Mitch? Yeah. Okay, there we go. Which is a SVG plugin for Grasshopper.
Just explain why we call things animals at all.
Oh, I don't know, Grasshopper, right? Is there a reason behind it?
Well, Rhino. So
here we go.
So Rhino and Grasshopper is kind of something that we have to put up with in terms of naming, and we came up with the idea of Wobbegong, the name for Wobbegong, one conference when a lot of very professional-looking academics were standing up talking about using kangaroo and ladybug and honeybee with rhino and grasshopper, and they just sounded like absolute loonies. So we decided to go for Wobbegong, which is a small shark that lives off the coast. A lot of surfers have to deal with it. It's an Australian animal, and it was more so just so that one day in a conference someone would say, talk about Wobbegong, and everyone would sit going, oh yes, oh yeah. So yeah, that was the reason why we went for Wobbegong, and these guys sort of stuck with the marine theme.
I think it was called Humpback at first because like humpbacks go all around the world, and it was like a GIS plugin, and then we just had to name the rest after whales.
And
we had to.